Can you please start recording? Perfect. Well, thank you everyone for being with us. We are very excited for presenting this webinar series, workshop series to all of you in application of AI for water management. And in the first couple of webinars we had, we set the stage on what is AI, how can we use it for water management, and kind of set the stage for diving deeper into the details of uh, AI modeling and the methods that are used for doing the predictive analysis. In this webinar, in this workshop, we will be getting more into the details of the mathematics and how the ANN, artificial neural network, is utilized for AI modeling and analysis and predictive analysis. And we have a very renowned presenter. We're very excited and we're very honored that he was available to present these details to us. A little bit about our panelists today. Emery, you probably are familiar with him. He's president of NOAA Global Solutions, who has been the leaders in application of AI in water management. And they've been doing this for the last 20 years. So it's not a new expertise that we're providing here. Myself, I'm the founder of Apex. So our role in the industry is to bridge the gap between the tech sector and the water industry sector, and kind of consult the water utilities of how to utilize AI tools and automation tools. And we have Michael with us from the CEO of Akaix, founder and CEO of Akaix, a leader in application of data management and data warehouses for water industry. They have developed very interesting platforms and very powerful platforms that have been utilized by water agencies for their data management. And a little bit about Sidar. He's the vice president of NOAA Global Solution, and he's a renowned mathematician and economist that is teaching in University of Budapest, and he has been working with the pioneers in the field of with pioneer mathematicians and Nobel Prize winners in the area of economics. And to say the least, he has published 25 reference books in the area of mathematics and formal optimization. And it's a very powerful presentation that we provided for you. With that, I'll pass it on to Sidar. He'll be presenting the rest of the presentation.
Actually, I'm going to just do a short introduction before we get into the mathematics of Dr. Sitarski, or Sidar as he likes to be known. So artificial neural networks is a really powerful paradigm that now everyone is aware of on some level because of all the public applications received in recent years, for example, in facial recognition. But there's a very deep mathematical history behind it, and it didn't just emerge out of nowhere. It goes back, some of the mathematics date back more than a couple hundred years or so. And that's what Dr. Sitarski is going to elaborate on. But first, again, I'll set a little introduction to how it evolved in terms of computational intelligence. Next slide, please. So humans have always been very consumed with where does thought come from? Where does our consciousness come from? And even Aristotle considered the question, which is not surprising. And he thought the brain was actually used to regulate the temperature. He thought thinking and thoughts came from and feelings came from the heart. But over time, of course, scientists have come to understand that our existence in terms of our actual awareness, that we're entities and we have thoughts and feelings and motivations, that does come from the brain over many, many hundreds of years of studies and contemplation. The brain that's pictured there is probably the most famous brain that was ever removed from a person. That was Albert Einstein's brain. That was actually just removed probably 5 miles from my house at Princeton Hospital after he died. And interestingly, just very quickly, it's not necessarily really germane, but there is some relevance. They did find apparently structural differences in his brain that they believe may have enabled his incredible mathematical and physical science abilities. To the right is the actual structure of what we understand to be how the brain operates. And within that figure are encapsulated three different Nobel Prizes. The first Nobel Prize had to do with the neurons, and that was identified as the building blocks in the late 1800s of the brain. The next Nobel Prize has to deal with synapses, and those are synaptic connections that allow the signals to be transmitted from one neuron to another neuron. And the third Nobel Prize has to deal with the process of how those impulses are transmitted through a combination of electrical impulses and chemical impulses. Next slide. So in the 1900s, there were some psychologists and mathematicians that were interested in understanding how does the brain operate. And that's where the foundation or the beginning of artificial neural networks as we know them today evolved. So essentially, they constructed a very crude mathematical representation of what we believe is the human brain. They connected different neurons or nodes with synapses, and these nodes are actually mathematical inputs into each of those nodes. The synapses or those connections between the nodes are mathematical functions that consist of weights. And during learning of the artificial neural network, those weights are iteratively adjusted to reduce the error between what the neural network is trying to learn and what the data actually presents itself to be. And as Dr. Sirausky is going to present, this involves a complex mathematical foundation of history of theory and application in order to allow these mathematical neural networks to learn and process data effectively. Next slide. So there's no shortage of applications of artificial neural networks. As I said, there's facial recognition. They use it for increasing or improving weather forecasting. It's used in the stock markets, airplane control, cars. So Tesla uses artificial neural networks as part of their deep learning to learn how to try and navigate the cars through traffic. It's even used by Major League Baseball teams for analytics. It's used in conflict resolution. And this photo is, of course, famous Babe Ruth with Ty Cobb, who were two giants in baseball who had no shortage of conflict between the two of them. So the next slide. So where is AI used in water? Well, it's been used in a number of applications. So we can use it to minimize human health risks by optimizing, for example, pumping rates of public supply wells that might be vulnerable to contamination. Be used to try and minimize overdrafting the aquifer, or it certainly impacts to environmental systems. So for example, trying to maximize the pumping that's feasible without dewatering wetlands or streams. It's been used to address climate uncertainty. You can use it to minimize energy costs. So there's a whole slew of activities in which it can be used for physical-based problems. Then it can be used for billing. It can be used for looking at customer usage rates. It can be used for optimizing the water quality. So there's no shortage of ways that AI is used in water, particularly since water has such a proliferation of data in these days. Next slide. So why do we care about using it in our field of study, water resources, hydrology? Well, because fluids is by itself a very, very complex phenomenon in terms of how fluids flow and move. And this is a quote that I like. It was a physicist that wrote a book about the physics of baseball. He's a very acclaimed physicist from Yale. And he quoted a very prominent physicist, he wouldn't name him, who said that this physicist believed that in his lifetime we would understand the Big Bang, but we would not understand why a baseball actually curves. Next slide. So why is fluid so complex? Well, we do have the Navier-Stokes equation, which is the foundational theory for how we model fluid, for example, climate, ocean currents, groundwater flow, the flow in the blood, flow of blood in your blood vessels. So the Navier-Stokes equation consists of two equations. One is known as a continuity equation, which is basically says that you're not creating or destroying mass within a unit volume. And the momentum equation is essentially Newton's second law, which is force equals mass times acceleration. And without getting to the mathematics here, you can see it's a rather complex equation or sets of equations that while they can be solved for a variety of applications and problems, they do have limitations. There are some problems for which they cannot find a solution or for which the solution simply blows up under some certain conditions. So next slide. So on that note, There's actually a prestigious Millennium Prize that was offered, I believe, in 2000, where there were 7 unsolved problems in mathematics. And the Clay Institute offered $1 million prize for solving each or any of those problems. And one of them is to solve the Navier-Stokes equation to show that it's actually stable under all conditions and can be solved for any different set of conditions, or to converse to show that it will not be solvable under all conditions, showing that mathematically in a rigorous format. The next slide. So my last slide is in groundwater or other fields, we often make very simplifying assumptions about the physical system, how the water might be moving or the fluid is moving. So a very typical assumption we make in groundwater flow, for example, is that we have laminar flow. If you're in a bedrock system or a karst system, that often won't apply. We also often assume that the system is very homogeneous and isotropic. And this is where the power of neural networks can come into play to try and simulate and model these very complex systems where there's a lot of data uncertainty and there's a lot of deviation between our physical-based models that are simplification of the real world and the actual real world. Next slide. So now Dr. Sidorowski will take over from this point.
So this is a neural network structure. There are the input variables are with these points. Here the output layer where the output variables are placed. And in between, there in this figure, there are two hidden layers. So you can see what is happening here. Each node in the first hidden layer is connected to all of the input nodes. From the second hidden layer, every node is connected to every node in the first hidden layer. So they are pretty much mixed up together. And the output layer, every node in the output are also connected to every node in the second hidden layer. So this is a very general neural network structure. So two things what I want to mention first. The first is that everything is related to everything here. It has a very important consequences. So simple cannot have a simple regression formula connecting the output, each output variable with the inputs. Because the inputs are not connected so badly than in a neural network. So if you do the regression analysis for each output variable, then you cannot take into account the inner relations in between those variables involved. So this is a much richer, much more rich description of the input-output relation. The second thing is, in the figure shows that all these relations are linear relations. So it means that H1, the first element, this is only a single hidden layer model. Each one is a simple linear combination of the input variables. It means that each input variable is multiplied by a constant and added up. And the same thing for the output. For each output variable is a linear combination of the hidden layer variables in a case that this is multiplied by a constant, the second one multiplied by another constant and added up. And this gives you the output variable. So mathematically, next please. So mathematically, the hidden layer variables are combinations of the input variables, and the outputs are combinations of the hidden layer variables, where these W's and the W bars are unknown up to this point. So if you combine these equations, you can get a direct input-output relation in the following way. That Y1 equals this W times H1, but you plug this H1 into here. The second term is a W coefficient multiplied by H2, but H2 is here. You write it there. And then rearrange the terms. You come up with an interesting combination of the unknown weights times the first input variable plus an interesting combination of the weights times the second input variable and so on. So we get both output variables and linear combinations of the inputs, but they are not independent of each other because the same coefficients are shown up in these equations, in y1 and y2 equations. So that is the reason why y1 and y2 is highly related. These common coefficients make the interrelation in between the two variables. So this will be how we will start the neural network mathematical issues. Next, please. Okay, so the question is always which kind of weights will describe best the actual model what we would like to model with this neural network. So best fitting coefficients needs to solve an optimization problem. So for the optimization problem, we need to create an objective function, which is an overall discrepancy between the measured and computed values. We will get into it in detail a little bit later. And the usual method that the people use for multivariable optimization is the gradient method. We will get to it a little later. Next, please. Okay, so to go to do this optimal method, we need definitely the partial derivatives of the objective function, and we need a matrix containing the second order partial derivatives. This is known as the gradient vector. That is known as the Hessian matrix. Next, please. There is a very famous theorem which was growing up from mathematics. And a lot of people, or some people at least, believe that Kolmogorov theorem gave the foundation of neural networks. As Emery told earlier, the idea of neural network was coming from the actual way how the brain works. So the neural network, discipline, came out from biology. There's no doubt about it. And absolutely independent, even decades before neural network was developed, Kolmogorov had a very interesting mathematical discovery. Next, please. One of the most influential mathematicians of the 20th century was Hilbert, David Hilbert. He was a universal mathematician, like a Renaissance scientist. So he did many, many different things in many different branches in math. But in the Second World Congress of Mathematics in Paris, he came up with 23 problems that he believed they should be what the mathematicians in the 20th century should be focusing on. So one was his conjecture, his thinking, if you have a continuous function with three variable continuous function, can it be rewritten as a superposition of continuous function of only two variables? This seems, from one side, an interesting mathematical question, but from the other side, it might have some practical interest also, because dealing with three variable function is not very easy. But if you can rewrite this a composition of smaller number of variables functions, then this is easier to deal with, two variables. So means you have to deal with two variables several times, and it is equivalent by dealing with a three variable function, which makes the things mathematically much easier. Hilbert thought it is not possible. As Kolmogorov proved otherwise. Next slide, please. So he proved the following. I know these mathematical notations, I will avoid it. So consider an n variable function. An n variable function, f of x, where x has n variables, x1, x2, and so on, k variables, x1, x2, and so on, xk. He proved the following. If you have any multivariable function, it can be decomposed to this formula. So what it means? Here, you have a given single-dimensional function. You substitute the variables, the individual variables, into the single-dimensional function. Then you get the terms from this summation. You add them up. Then you get a number for ej. So then you plug these numbers again into single-dimensional functions. And then you add up the values of the single-dimensional functions, and it gives you the value of this multivariable function. This is sort of an interesting stuff, but shows a lot of advantage. Dealing with single variable function is easy. If you took a first semester calculus, you know very well that every interesting properties of single variable functions can be obtained easily. Take the derivative, its positive function increases, its negative function decreases, second derivative is positive function is convex, and so on. So it's very easy to deal with. But with multi-variable functions, it is not so easy. Because from a point in the single dimensional, you can move to the right or to the left. In the bivariable case, from the point you can move to infinitely many directions. And to handle all of these directions mathematically, it's a very difficult task. So dealing with multivariable function, this kind of decomposition might help a lot. Next, please. Okay, so I will go a little bit into the history of mathematics to see how these things were coming up, which did lead to Hilbert's 23 problem and for Kolmogorov result. There were several directions which has grown up in the end of the 19th century and beginning of the 20th century. The first was foundation of mathematics. People realized that our language is not precise enough. So any science, no science can be built on only our language. Let me say a sentence. I always lie. This has a contradiction in itself, because if I am lying now, then my statement is not true. If I am telling the truth now, again, my statement not true, because this time I am not lying. So, and there are many, many things in the languages which might lead to strict contradiction. So it means in mathematics, as every science, we can exclude the possibility of this kind of contradictory stuff going into. Because it's a fact, if I have a contradictory system, I can prove everything. So it doesn't have any sense to have any contradiction in any system. So first, an Italian mathematician, Giuseppe Peano, was creating axioms for the natural numbers. All these axioms are common sense stuff, but postulating them as axioms and building on these axioms make everything very rigorous. So this would be a possibility to exclude those kind of problems with the language and the human brain might create. Some axioms are really very simple and primitive. Even a non-mathematician would start laughing on it. First is 0 is a natural number. Fine. Every natural number has a next one. You n, you have n plus 1. And some others, very, very trivial stuff. Geometry had also a problem, because the Euclidean geometry had the parallel axiom. It means you had a straight line, you had a point outside it. There you could have exactly one straight line which goes through the point and parallel to the given line. That was, everybody believed it, but there was a Hungarian mathematician, Bolyai, János Bolyai, who dropped this axiom, and he assumed that we might have several parallel lines, and he built up a very new geometry. It turned out it has even an important role in the Einstein's relativity theory. Axiom of choice by Zermelo was again a very simple axiom. It's a common sense. If you have infinitely many sets which are mutually exclusive, you are able to select one element from each of these sets to form a new set. That's, again, an absolute triviality, but this statement, this axiom, was one of the basic axioms of modern seed theory. This was one line. The other line is mathematicians would like to do everything as general as possible. So they started introducing and examining general structures. Very first comes into our mind, if you consider numbers, you consider vectors, matrices, functions, you can always define an operation in between, like adding them. Additions of number is clear, addition of function value is clear. You can add up vectors when they have the same length. You can add up to matrices if they have the same size, same style. So what mathematicians did, they simply introduced a new structure where they did not care what the elements are, but there is one kind of operation among the elements. And they started investigating, and a whole new mathematical field came out, which is known abstract algebra. You know, in calculus, you need certain measures. So people started introducing certain abstract spaces where some measure was introduced, like distance between 2 points. They called as metric spaces. Nothing else is assumed, only you have a bunch of points in a set, and there is distance defined in between 2 sets with certain very trivial axioms. Also, a whole lot of theory built up from metric spaces. They could be refined, as they call as a Banach spaces, and also one of these special spaces are called the Hilbert spaces, where the basis is the inner product of element, like if you multiply a row vector by a column vector, you get a number. So if you have a special product between 2 elements where the result is a number, this is inner product. And inner product spaces, it could be proven. The Banach special case of the Banach space is also a special case of the metric spaces. A whole lot of literature was written. A new scientific area, functional analysis and operation theory, was built out of it. The next area which was developed, it was probability theory. Probability theory, again, it was originally based on human thought, which was not precise, and a lot of trouble came out of it. Kolmogorov was the Russian mathematician. We will learn about him a little bit later. So Kolmogorov, who simply set up axioms of probability. There are 3 axioms, which are also very trivial. It means every probability is between 0 and 1. Between 0 and 1. Let me tell you a funny story. I had a student in Tucson who missed a homework, and he told me that he will turn in the homework next week. Did not do it. I met him, I was telling him. He told me next, Professor, I promise you, I will return the homework 200% sure. I told him, with this 200 sure, you flunk the exam. Because probability must not be larger than 1. So the axioms are also the impossible event has a 0 probability. If you have 2 events which can never occur together, then the probability that at least one occurs is the sum of the 2 probabilities. From this very simple axiom, a whole new mathematical field, probability theory, was coming out. In optimization theory, the very simple optimization problem is linear programming. Kantorovich, in 1939, he discovered the simplex method, which is today the well-known method for solving linear programming problems. He was in the Soviet Union that time, and Stalin, he ordered to make an optimal management of the Soviet agriculture. So they made up some model, and they had to solve it. So Kantorovich worked out this method, and it became completely unknown, because he wanted to publish this method in a very famous Russian mathematical journal, Doklady. It was practically rejected by the editor. They did not even want to deal with it. And in Hungary, there was a rumor about it, that this poor guy was called into the party office, and they asked him that how the genius ideas of Comrade Stalin are involved in your methodology. So they simply rejected the paper. Finally, next year, it was published in a not so good journal, which became completely unknown. The beginning of the 70s, somebody discovered it, and he got the Nobel Prize in economy. That was about optimization. Game theory is, again, a relatively new field. John von Neumann wrote a paper in 1928 where he practically defined the equilibrium, what Nash defined in his 1950 PhD dissertation. So some people were much ahead of their times. So we go now to the field of applied mathematics. In applied mathematics, don't forget at the beginning of the 19th centuries, or the end of 19th century, beginning of 20th century, there were no computers. There were no other than either this simple mechanical calculation way or abacus, when you had a string and a lot of balls there, and you had to pull those balls. This was the way to calculate. So doing complicated calculation was very, very difficult. The first time when they published an exponential function table, the company who published it, they raised a huge money if somebody finds a mistake in it. And after after about a year, nobody came out with any mistake. Then they widely accepted this table is correct. How they worked? 3 people were calculating the same entry into the table. 3 people completely independent of each other. And they accepted this result when all the 3 people got exactly the same answer. Otherwise, they recalculated it. So the simplification thing was very, very important. So I show some example when simplification had a role. If you have a linear system of equations, it can be written as a matrix times the unknown vector equals a right-hand side vector. So if it is a full matrix, the solution is not too easy. There are certain elimination processes. It is not a very easy job. And also the round of error accumulation might kill the results. However, if the people were transformed the matrix into diagonal, then everything became easy because the first equation became A1 times x1 equals B1, second equation A2 times x2 equals B2, and so on. And these equations could be solved by simple division. So we did not need to do complicated computations, so it did not lead to doing lengthy calculations. This was very simple, finally. Same happened with differential equations. If you had a homogeneous first-order linear differential equation, again, you had a coefficient matrix. If it was a full matrix, getting the solution, probably you had to get the eigenvalues, eigenvectors of the matrix. You had to get the matrix exponential for this matrix, which was a very lengthy and painful job. Instead of, if you could transfer the matrix at the beginning to diagonal, then every equation became the same structure. So you really have to solve a single-dimensional first-order equation, which is a very, very simple task. Next, please. Linear programming. Linear programming means you have a bunch of constraints about the variables and you want to optimize an objective function. So if you make a small figure where the 2 variables are the two coordinates, then you can show that this set, what I show here, this set is the set of all feasible solutions. And if we have to maximize or minimize a function on this big set, which has infinitely many points, it is a challenging issue. But what Dantzig and Kantorovich showed, that if we have an optimal solution has to be at one of these vertices. So in this case, we have 4 vertices, 0, 0, 6, 0, 3 over 2, 3 over 2, and 0, 2. So we simply have to consider these vertices and substitute them into the objective function, and we can see that 2 is the highest value. Therefore, 2, 0, this point gives you the optimal solution. This was a tremendous development tremendous development. Next, please. Okay, the next is in linear optimization problem, the gradient algorithm use. So how it works? You take a point, an initial point. You take the gradient. Gradient, it is a vector which consists of the partial derivatives of the objective function. It gives you a direction. So now you have a line, a one-dimensional line. And then you optimize the objective function on this line. Let's say this is the optimum. Then you recalculate the gradient, you get a new direction, and this new direction you optimize again. And if you do it iteratively, under very general conditions, this algorithm does converge to the true optimum. So what was the simplification here? At each step, we had to deal with only a one-dimensional optimization, There are many, many search methods, very simple search method to get the optimum. The next one is if you have to solve a bunch of nonlinear equations with many variables. There is no very good software getting it to you, but there are very good software to solve optimization problem. So we can rewrite it as an optimization problem. Consider a new objective function, which is the square of the first left-hand side plus square of the second left-hand side, and so on, the square of the last left-hand side that you want to minimize it. Since we square them, every square is non-negative, therefore the new objective function is non-negative. So there are two possibility. First, if the objective function at optimum gives you 0 value, it means that if the sum of the squares is 0, it means that all these values should be 0, we got a solution. And if the optimum objective function gave you a positive value, it shows there are no values where each of them is 0, because otherwise the objective function would become 0. It would contradict to the positive optimal value. So it shows that there is no optimal solution, or there is no solution for this set of equations. The next one is the Newton's method, what everybody knows. If you have to solve a nonlinear equation, the usual method is the following. You take a point on this curve, you take the tangent line, and you see where the tangent line crosses the horizontal axis. You go up to the curve, you do the tangent line. Even from this figure, you see it is pretty soon does converge to the intercept of the curve and the horizontal line. It means where this function has a 0 value. Next, please. Okay, so let me remind you for the Kolmogorov theorem was that if you have any, in this case, n is the number of variables, if you have any n-dimensional function, it can be decomposed this way. We can have a simple diagram for this. So consider these points are the input variables. They go into a sort of kind of mixing operation, and if you plug, so here you do this mixing. You get these functions, these function values, and you add them up. For the J's, it has 2n plus 1 nodes in the hidden layer. So here you make these function values, you add them up, you plug it into the gave G function, and this will be one term in this summation. You do the same thing for G2 and so on, and you add them up, and this is your function, this is your output. So it can be considered as a primitive neural network where the input variables are. The axis, this is actually the middle layer. You can consider it either 1 or 2 middle layers. Here I set it up as 2. And then they are added up, combined into the output. So Kolmogorov theorem really has a very nice illustration of neural networks, and it has several very important consequences. So let me talk about them before going further. The neural network, as you see before, it has only linear functions. But here, you need nonlinear functions. It is a well-known fact mathematically that locally you can approximate any nonlinear function as accurately as you want. Also, introducing some additional linear functions, you can model piecewise linear functions, Broca-like functions. And it is very well known that in any continuous function can be approximated arbitrarily well by piecewise linear functions or Broca-like functions. So it means that introducing these linear relations between the different variables, and if we select them appropriately, these functions are approximated very approximately. It means that we can get this function value very accurately. So in pure English, plain English, I could say, if you introduce sufficiently many functions, and these many functions are combined into these phi's and g's, in this case, you can represent a multivariable function almost accurately, which is coming out from Kolmogorov's result. So now question is, how can we get next one, please? Okay, so I keep this guy. So they are the G values, which are linear combinations of the two input variables. And also the output is a linear combination of the two G's. So in here, we have 6 unknown parameters: the two A's, the two B's, and the two C's. So how can we get the best fitting values? So now it is called as the training of the neural network. Means you take a lot of historical data, a lot of past measurements, where you measured the two input variables and also the corresponding output variable together. So you have a bunch of such measurements. So you have simultaneous measurements for the input and the output variable. Here, I talk about one output, but the same if you have several outputs, then you have several outputs, similar relations. So now we do two things. One thing is, we consider these as the input variables, and we use the input-output relation that the neural network gives us. This is the same thing what I showed before. So if you substitute G1, this G1, into here, you substitute this G2 right here, you come up with a direct input-output relation. So if you simply substitute a simultaneous x1, x2 values into it, this function value will clearly depend on the unknown parameters. But you know the true value. You know the true value. So what you can do, you can get the error. The error is you can have the computed value, you know the measured value, you take the difference, and you square them up, and you add up the squares of it. The reason why you square it, because if you simply add up discrepancies, there are some positive, some negative, they cancel each other, so you might come up with almost no error. But if you square them up, they will be positive. This is clearly a nonlinear function of the unknown coefficients. It is actually a 3-variable function that you have to solve. And you can use the gradient algorithm that I showed before. This is backpropagation, how they sometimes call it. It is exactly the same as using the gradient algorithm for this very special objective function. Next slide, please. So if you use a bunch of data and get the best answers, and you simply get the error also, because this is the optimum value of the objective function, then you get a feeling how good it is. But it is not good enough. So what people want to also verify validate those coefficients what you get. So what you do, you use about half of the historical data to get the best values of the coefficients, and then you take the other half of the historical data, and you recalculate that objective function that I showed before, but there is no optimization because you already have the coefficient values that you got from the neural network training. So you get an overall error, which validation. You have to be careful a little bit. because you must not select the very beginning for the data for training and from the very end the data for, because in this case they are not independent. So you have to select about half of the data randomly selected from the data set. And the leftovers will be used for validation. And if both validation and the optimum gives you a relatively small overall error, usually you know how accurately you want to have the neural network, so you set up a threshold, error threshold at the very beginning. If both are below the threshold, you have all the reason to believe that your neural network is pretty good. One thing that we have to be a little bit careful, because you are adding up values. And if one of the input value is huge, the other input value is very small, if you add them up, really the effect of the small one disappears. So therefore, before getting into the procedure, we transform all the input data and also in the hidden layer values into the same interval between 0 and 1, and sometimes between -1 and 1. And it is very clear that if x any positive or negative number, this will be clearly between 0 and 1. You get close to 1 if x goes to infinity, because e to the negative infinity is 0. And if x is 0, it is 1, you get 1/2. And if x goes to negative infinity, then it is e to the positive infinity, which is infinity, 1/infinity, 0. So in the two extreme case, it goes to between 0 or 1, and in between these two values. And very similarly, it can be shown that the values of this transformation is always between -1 and +1. So this kind of neural network can be used for many, many things. One thing is, if you have an optimization problem and you have to use a certain hydrologic kind of equation there, but you cannot have analytically. But you have data. Then you can replace the analytic form of the function by a neural network, and you can append this neural network into the optimization problem. You can use it for prediction, because assume you have some variables that you can predict, but some other variable that we can consider as output, you cannot predict directly. You don't have access to it or certain reason. So in this case, again, you create a neural network, and the prediction for the output is done easily. You simply predict the input variables, you plug them into as input variables into the neural network, you run the neural network, you get the output, and this should be a very reliable prediction for your variable what you want to do. So neural network based on the Kolmogorov result is able to approximate phenomenon based on historical data, natural phenomenon, or any kind of physical relation as accurately as you want. This is very, very important. So you don't lose accuracy because choosing this method. Next, please. Some advantages. First is it can learn accurately, to accurately responses to complex system. Then the condition is you have to have access to data. And some of the people feel uncomfortable with neural network because they consider neural network as a black box. It is not a black box. It contains all information that happened earlier about this phenomenon. So with the data, it is based on the data. Therefore, it does not contain any equation or very, very beautiful stuff, but it contains all the information that the previous data would provide. So physical-based models also have a problem. Any kind of mathematical model has a problem. Because if it is a very simple model, you can solve it easily. But if you get a simple model, you have to neglect a lot of factors, a lot of important things from the model. So if you oversimplify it, your model has practically not much relation to real world. The other extreme is if you overcomplify model. If it is a very complicated model, it's very nice. It would describe reality beautifully, however, you cannot solve it. So somehow the right model type and size and the combination level should be, I would say, creating a right model is not a science. It is more than an art, more an art than science. And also, it can be very fast because the relatively simple equations you are doing repeatedly, so you get answers very fast. It means that you can use neural network online. When your calculation is based on measurements, you get new measurements, you retrain the neural network in thousands of a second, you get the predicted values. And also, as I mentioned already, can effectively, efficiently be coupled with formal optimization if you want to have advanced decision maker. A lot of decision-making problem arises, a lot of. If you have cost involved, any kind of cost, if you supply the water from different resources, which kind of optimal combination what you have to use. Also, if there are some environmental issues, salt water intrusion, also you have to use neural network definitely to see how the intrusion can be stopped. So in this case, you have to predict with a neural network the pressure inside that underground water reservoir, because the inside pressure must not be smaller than the outside pressure, because otherwise the outside water is coming in. So that I could continue until tonight, midnight, with these kind of examples and things what we did, but I rather give the chance to Emery to talk a little bit.
Emery,
We didn't hear you.
Excuse me, I'm sorry. Thank you, Sidor, for that very comprehensive and detailed overview of the power of neural networks mathematically and how, even though they were, like as you say, inspired by biological understanding, they have a very rich mathematical foundation that underpins their operation and their power. And I know we went a little bit later than planned, but if there's any questions from the audience, please feel free to ask. Has
Well,
anyone come up with? Yes.
I do want to go back to that the advantages of ANN slide. And if you can please explain to us and compare the ANN, talking about the advantages, the one before the last slide, the advantages of ANN compared to numerical modeling. As you know, in groundwater industry, we use a lot of numerical modeling, ModFlow, to do a lot of our analysis. How do you compare ANN compared to the numerical model?
Let me
They
tell
both have, yeah, go ahead, Sidor.
one actual example what we did. I don't want to tell from which watershed, but when Emery was working on his PhD dissertation, we got some data from that watershed, and the water levels had to be estimated. So they had a very complicated program, but they spent millions of dollars to develop this program. They ran their programs to estimate the water levels. Emery came to my office with his laptop. I gave him the data on a disk. He read it in. He was training the neural network for about 10 minutes, and he was doing the predictions, which was one order of magnitude better than the professional software.
So yeah, so the magic of the neural networks is you don't need to concern yourself with all the hydrogeophysical parameters. So the neural network doesn't care what the transmissivity is, what the storativity is, where is the clay layer, does the clay pinch into silt? It's only concerned with what the data shows itself as a manifestation of physical systems. So for example, if you pump the aquifer more, the water levels will clearly drop more. If there's a lot of rainfall, the water levels might rise. But the hydrogeologic parameters that influence those effects are taken out by the neural network. It's directly learning from historical data how the water levels respond to different inputs. So for example, the rainfall, the temperature, if they're pumping groundwater, if they're recharging groundwater, that's all embedded within the data. The neural network processes that data and learns those relationships mathematically. Somewhat like our brains, when we're looking at some phenomenon of nature, we may not understand all the underpinnings of why the nature is behaving that way, but we've come to recognize certain patterns, and we can then anticipate and very accurately predict what might happen next, just based on our historical experience and our ability to process patterns.
Wonderful. Yeah, that's a very powerful feature that ANN has. And as you mentioned, we don't need to understand the physical parameters of the system. We just need the manifested data. That's a very good term. I really like that you use that manifestation of the data for the system. We're running out of time, and I don't see any questions. Thank you, Dan, for your comment. If there's no more question, we just some housekeeping stuff. We have the next AI workshop that we have is going to be on generative AI and how we can utilize tools like ChatGPT and other Gen AI tools for better water management and better productivity, basically. And the recording of this presentation is going to be available. We will be following up with you, and the date of the next workshop is still to be decided. We will let you know in our follow-up email. Thank you, everyone, for being here, and hope you have a great rest of your day.
Thank you.